This is Calculus 2 video lecture number 8 on arc length. So we're going to begin our unit on further applications of integration by looking at how to compute the arc length for a function in two-space. So suppose the length of the curve y equals f of x from the point p0 to pn is L. So notice we have a function f of x graphed in the plane, and the curve, the function, is in blue. And its length is L. And we want to compute the length of that curve as if you were to take the curve and stretch it out completely straight and then measure it. Well, what could we do? Well, we could come along and chop it up into a bunch of little line segments, and then we could compute the length of each segment really easily, right? Because if I have 2 points, say P0 and P1, or P1 and P2, then I could just use the distance formula and figure out the length of each of those little line segments. So we chop up the interval from A to B and into n many pieces. And each of these little partitions has length delta x. Okay. And notice here, this is just an approximation. So obviously there's some error if we were to sum up the lengths of the line segments and compare it with the actual length of the curve. And so in order to improve our approximation, we can just take more and more line segments. We could let n get larger and larger and chop it up into tinier bits. That way there's less error. Well, we're in calculus, so why stop at a finite number? Let's just let n go to infinity. Let's have infinitely many little line segments, and then our error will approach 0. And that's precisely where the formula for arc length comes from. So we can write it in the following form: the limit as n approaches infinity of the sum, and these are all the little line segments. This is some arbitrary ith line segment. So we're summing them all up from I equals 1 to n, and we're taking the length of each of those. Okay, now using the distance formula, like I mentioned earlier, we can compute the length of the ith segment. Remember, to use the distance formula, we need to know what the coordinates are for each of those points. So let's go back to the graph here. We're working with the ith line segment. So I want to know what the coordinates are for p sub I minus 1 and p sub I. So p sub I minus 1, can you see where it is? It's right here. Its x coordinate is x sub I minus 1. And the y coordinate would be y sub I minus 1 also. And similarly, p sub I has coordinates x sub I, y sub I. Can you see that here? X sub I, and then it would be the y value there. Okay, so let's put this all together. So that means the length or magnitude of line segment p sub I minus 1 to p sub I, this here, is equal to the square root of, I have x sub I minus x sub I minus 1 squared plus y sub I minus y sub I minus 1 squared. All right, and then notice x sub I minus x sub I minus 1, that's just delta x, right? We chopped up the interval from A to B into n many pieces evenly. Now, can I replace y sub I minus y sub I minus y sub I minus 1 with delta y? No, not quite. Look back at the graph. Notice delta x is consistent, right? For all of our partitions, we evenly space them out. But delta y is not the same for every interval. Here, delta y is large. Here, not so large. Here, it's negative, a little more negative. So delta y depends on I. It depends on which partition you're in. So what I'm going to mark it or replace it with is a delta y sub I squared, since that one's changing. Okay, we're going to put this portion on hold, and then we're going to use the mean value theorem now to help us proceed with getting the formula for arc length. Do you remember the mean value theorem back from your Calculus 1 days? Well, remember, the mean value theorem tells us, as long as f is continuous and all that good stuff, that on the interval from A to B, we can find some f prime of C that is going to equal f of B minus f of A over B minus A. And just remember this graph, it'll help you understand the mean value theorem. The right-hand side that I've written here gives us the slope of the secant line that goes through the function y equals f of x, which is shown here. This is y equals f of x. Notice the blue line gives us the slope of the secant line, change in y over change in x. And the mean value theorem tells us that we can find some c that's on the interval from a to b where the slope of the secant line is going to equal the slope of the tangent line at c. And notice they're parallel, right? Okay, why am I bringing this up? Well, look at what's going on at each of these little partitions to our curve. I'm going to focus in right now on the ith subinterval. And here we have a secant line. Oh, yes, we do. This is the secant line right here from p sub I minus 1 to p sub I. Could we get the slope of that secant line? Well, remember, slope is change in y over change in x. Change in x I know is delta x. Change in y is going to be delta y sub I. And by the mean value theorem, I know I'm going to be able to find some point. Normally we call it c. I'm going to call it x sub I star, where the slope of the tangent line is equal to the slope of that secant line. So that purple line I just drew has the same slope as that little line segment from p sub I minus 1 to p sub I. And I know I can do this at every subinterval on this curve because of the mean value theorem. So that means f prime of x sub I star is going to equal, remember this is the slope of the tangent line, is going to equal the slope of the secant line or line segment, which is rise over run delta y sub I over delta x. This is slope of the line segment. But what was the point of this? Well, now I can rewrite delta y sub I equals f prime of x sub I star times delta x. Ooh, wonderful. Now I'm going to put this back into the distance formula where I was finding the length of each of those little line segments. So, revisiting, I know the length of segment p sub I minus 1 to p sub I is equal to square root, and then remember we had delta x squared plus delta y sub I squared, and then now I'm going to replace delta y sub I squared with this expression here, f prime of x sub I star times delta x. Here we go, exciting stuff, people. So this is delta x squared plus f prime of x sub I star delta x squared. Okay, I can factor out a delta x squared from the expression. So I have delta x squared times 1 plus f prime of x sub I star. That's still squared though. And then I'm left with square root 1 plus f prime delta x, oh no delta, excuse me, just x sub I star. This is all squared times, and then that delta x squared, I can pull it outside of the radical, and now it's just regular delta x. Woo! So I'm going to replace this in that original formula. Remember we had that the arc length was equal to the limit as n approaches infinity of the sum I equals 1 to n. And then instead of writing the length of p sub I minus 1 to p sub I, now I have this expression here. So this is going to be square root of 1 plus, let me switch to brackets, it'll look so clean, f prime of x sub I star squared times delta x. Well, I see a limit as n goes to infinity and a sum. That means we are going to integrate. Oh, yes. And here's your arc length formula. Dun, dun, dun. So if f prime is continuous on a to b, we need that because remember we used the mean value theorem to get this formula. Then the length of the curve y equals f of x on the interval from a to b is given by the definite integral from a to b of the square root of 1 plus f prime of x squared dx. All right, such fun. Now, if the curve has the equation x equals g of y, so if it's a function of y on the interval from c to d, and g prime of y is continuous, then the length would be the definite integral from c to d of the square root of 1 plus g prime of y squared dy. So let's try one out, eh? Here we go. Example 1, find the length of the curve. We have y squared equals 4 times x plus 4 cubed on the interval from 0 to 2, and they're telling us PS y is greater than 0. Okay, so to get started, let's solve for y. So y equals plus or minus the square root of 4 times x plus 4 cubed. And I know I'm going to choose the positive radical because they told me we're interested only in the portion of the curve where y is greater than 0. So that means y equals 2 times x plus 4 to the 3/2 if I take the square root of everything. Now what I like to do is all my prep work ahead of time, meaning I'm not going to write out the full integral yet. I'm going to figure out what f prime is, square it, add 1, and get that all clean and pretty before I actually write up a full integral. Okay? So here we go. F prime of x, or dy dx, is going to equal, so I have 2 times, I'm going to multiply by 3/2, leave x plus 4 alone, subtract 1 from the exponent, so it's going to be 1/2. And we end up with 3 times x plus 4 to the 1/2. Okay, now remember the integrand was 1 plus f prime of x squared, so let's get that all ready to go. It'll make life easier. So we're going to have 1 plus f prime of x is 3 times x plus 4 to the 1/2, and then we're squaring that. Which means I'm going to have 1 plus, now be careful, this is 9 times the quantity x plus 4. If I distribute the 9, that's going to be 9x plus 36 plus 1, so this is 9x plus 37. All right, and now we're ready to roll. So arc length is going to equal definite integral, they gave me the limits right here, from 0 to 2, and then I have square root of 9x plus 37 dx. Okay, now hopefully at this point you don't need to do a u sub. You can just imagine if you were to u sub and let u equal 9x plus 37, du would be 9 dx. So you would have a 1/9 in the integral. So let's just take care of that. And then let's see here. So 9x plus 37 is raised to the 1/2 power. If I add 1, that's 3/2. And then I need to divide by the new exponent, which is the same as multiplying by the reciprocal of 2/3. And we evaluate this from 0 to 2. So fabulous. Okay, so 2/3 times 1/9, that's going to be 2 over 27. And then now I'm going to start plugging in the limits of integration. So 9 times 2, that's going to be 18 plus 37 to the 3/2 minus, and then be so careful, 0 plus 37 still 37 to the 3/2. All right, so we have 2 over 27 times, this is 55 to the 3/2 minus 37 to the 3/2. And then we can just rewrite our final answer, 2 over 27 times 55 rad 55 minus 37 rad 37. And nothing else distributes or cancels, so we'll just leave it like that. All right, how was that? Not too bad, right? Normally these integrals aren't too crazy like the ones in the previous unit. There's just like a few classic ones. So this is one of them, and the next one I'm going to show you, you need like this little slick factoring maneuver. But then once you see it again, you're like, oh, that old problem. So here we go. Find the length of the curve. This time x is a function of y. And it's y to the 4th over 8 plus 1 over 4y squared. Y is from 1 to 2. I'm going to rewrite it in derivative-friendly format as x equals, this is 1/8 y to the 4th plus 1/4 y to the negative 2nd. So we'll be ready to differentiate it. And in this case, since x is a function of y, the arc length formula we're going to use is the integral from c to d of the square root of 1 plus dx dy squared dy. All right, so let's take the derivative, clean it up as much as possible, and then we'll start integrating. So here we have dx dy equals, so now I'm going to differentiate this guy. So 1/8 y to the 4th, that's going to be 4 over 8 y cubed, minus 2 over 4 y to the negative 3rd, which is 1/2 y cubed minus 1/2 y to the negative 3rd. All right, beautiful. Now remember, what I integrate is 1 plus that derivative squared. So let's do all the prep work now. So 1 plus, now I'm going to square this quantity. So remember, you're going to square the first term. So you have 1/2 y cubed squared minus 2 times the product of the first and second terms, 1/2 y cubed, 1/2 y to the negative 3rd, plus then I square the last term, 1/2 y to the negative 3rd squared. I'm really breaking it down. I don't ever do it this way because I know the pattern and I can go more quickly, but this is just to show you guys for the first time. All right, look at this. So we have 1 plus, if I square 1/2 y cubed, that's 1/4 y to the 6th, minus, now notice, the 2 and this 1/2 cancel. And then we add our exponents. So y to the 3rd and y to the negative 3rd, that's going to give us y to the 0. So y's are gone. They cancel out completely. All I'm left with is a 1/2 from that term. Plus, if I square the last term, that's 1/4 y to the negative 6th. So this is what I get when I squared the derivative. Okay, anything else you notice we can do? Well, I see this 1 and this negative 1/2. Let's combine them, okay? And I'm going to write it now as 1/4 y to the 6th plus 1/2 plus 1/4 y to the negative 6th. So all of this is supposed to go underneath the radical. But remember, you want to make life as nice as possible for yourself. So is this a nice quantity to take the square root of? No, I don't think it is. And I want you to notice something. Here's the big trick to this problem. When we took this expression right here, the derivative, 1/2 y cubed minus 1/2 y to the negative 3rd, and we squared it and cleaned it up, we ended up with 1/4 y to the 6th minus 1/2 plus 1/4 y to the negative 6th, right? We ended up with this expression. And now, after I added the 1, I have this expression down here. We'll compare this with what we got when we multiplied out the derivative, when we squared it. The only thing that's different is I have a positive 1/2 here, and this was a negative 1/2, which means this is going to factor very similarly to how dx dy was factored before we squared it. So this is going to be 1/2 y cubed plus 1/2 y to the negative 3rd squared. And now we're ready to put it all together because I can easily take the square root of this and then anti-differentiate. Did you guys see that? Slick factoring. Okay, this is a classic problem. So the equation will change a wee bit, but the idea is the same. You always end up with that negative 1/2. You add the 1, you get a positive 1/2, and then you refactor with a plus. I kid you not. Okay, so putting it all together, the arc length is equal to the integral from 1 to 2. I have the square root of 1/2 y cubed plus 1/2 y to the negative third squared dy, which all cancels out, right? The squared and the squared root. So we have 1 to 2, 1/2 y cubed plus 1/2 y to the negative third dy. All right, we can take this 1/2 outside, so let's do it. So I have 1/2 times, now let's anti-differentiate. This is going to be 1/4 y to the 4th. Add 1 to negative 3, it's negative 2. So I'm going to divide by that. So negative 1/2 y to the negative 2nd. Evaluate this from 1 to 2. And now I have 1/2 times, let's see here. So 2 to the 4th, that's 16 over 4, minus 2 to the negative 2nd, that's 1/4. And I still have the 1/2. Minus, if I plug in 1, I have 1/4 minus 1/2. Okay, so this is 1/2 times 4 minus 1/8 minus 1/4 plus 1/2. Yay, fraction. So this is 1/2 times, common denominator is 8. You should end up with 33 over 8. So this is 33 over 16. Ooh. All right, I kid you not, you're going to run into that little classic factoring problem so many times. If you open any old calc book, it's in there. Just the exponents might be a bit different. Okay, but now you know. Now you know the trick. You can wow all your friends. I got one more example for you. Are you guys ready? Here we go. So find the exact length of the curve. Y equals the square root of x minus x squared plus sine inverse of rad x. What in the world? They didn't give us limits. That means we have to figure out the domain of the function and just use that domain to give us our limits of integration. So let's see here. I have a radical function with an even index. That means the radicand, or the stuff underneath the radical, has to be positive. So x minus x squared has to be greater than or equal to 0. How do you solve a quadratic or higher order inequality? By finding the zeros and using test points. So x times 1 minus x has to be greater than or equal to 0. That means on the number line, I'm going to list the zeros, 0 and 1, and test each interval. So if I pick something smaller than 0, say negative 1, and I substituted in negative 1, this would be negative, this would be positive, so their product would not be greater than or equal to 0. So nothing in that interval works. If I pick something between 0 and 1, like 0.5, that would be positive, that would be positive. So the product is positive. So anything in this interval works. And then greater than 1 won't work either. Similarly, sine inverse of rad x, again, x has to be greater than or equal to 0 because of that radical. So the domain for f of x or y of x is the interval from 0 to 1. So I'm going to use those as my limits of integration because the function or the curve only lives there. That's its domain. There's no other x values for which it's defined. So if they're asking for the length, those are my limits. So the arc length is going to be the definite integral from 0 to 1 square root 1 plus dy dx squared dx. So now let's go ahead, take the derivative. Okay, so dy dx, if I differentiate rad x minus x squared, anytime you take the derivative of the square root, you end up with 2, and the original radical expression in the denominator. And then by the chain rule, you can just multiply by the derivative of the radicand, or x minus x squared, in the top, so that would be 1 minus 2x. Plus, and then derivative of sine inverse of rad x. So it's going to be 1 over square root 1 minus radical x squared. So that just becomes x. And then by the chain rule, I have to multiply by the derivative of rad x, which is 1 over 2 rad x. Well, notice I actually already have a common denominator. Someone loved us when they wrote this problem, my goodness. Because rad x minus x squared is x times 1 minus x, which is exactly what we have over here. Rad x, rad 1 minus x, and we even have that too. So we can already add the numerators together. This problem's a dream come true. I have 1 minus 2x plus 1 times 1. So that's 2 minus 2x over 2 rad x times rad 1 minus x. Can we clean this up? Yes, okay, in the numerator I can factor out that 2, and then I have 1 minus x, over 2 rad x, rad 1 minus x. So check this out. The 2's cancel, and the rad 1 minus x is gone, and instead of 1 minus x in the numerator, now I have rad 1 minus x. Lovely. So this equals square root of 1 minus x over x. That's the derivative. Okay, well, what do I integrate? 1 plus the derivative squared. So that means 1 plus dy dx squared is 1 plus, if I square this guy, the radical's gone. So I just have 1 minus x over x. Let's add them together. Common denominator is going to be x. So 1 becomes x over x. So I have x plus 1 minus x over x, which is just 1 over x. Wow, this cleaned up big time, right? It's like extreme makeover. So the arc length L is equal to definite integral 0 to 1 square root of 1 over x dx. Now take a look at this guy. Is something jumping out at you? I hope so. This is an improper integral. If you forgot, it was just the previous video. Video number 7. Because 0 is not in the domain of the integrand. So what do? We rewrite it as a limit. So I'm going to write this as the limit as t approaches 0 from the right, because it's the lower limit. Integral from t to 1. This is 1 over rad x, or same thing as x to the negative 1/2 dx. I just like to rewrite it that way so I'm ready to anti-differentiate. So now we have the limit as t approaches 0 from the right. Antiderivative of x to the 1/2 is going to be 2 times x to the positive 1/2. I'm evaluating that from t to 1. So this is the limit. T approaches 0 from the right. Plugging in the limits of integration, you're going to have 2 times 1 minus 2 rad t. T is approaching 0 from the right, so this whole term's just going to go to 0. And I am left with 2. So that is the length of our curve. Woo! We made it. All right, so that concludes the lesson on arc length. Believe it or not, a lot is going to build on this formula in Calc 2 and even in Calculus 3. So make sure you do not forget the arc length formula. And I hope you enjoyed the lesson. Please give the video a thumbs up, subscribe if you haven't already, and next we're going to look at surface area.